grata oportunidad de presentar a Gerald Tenenbaum, que es profesor en el Instituto Elie Cartan de la Universidad Henri Poincaré en Nancy, Francia, especialista en teoría probabilística y analítica de números, y además de tener una producción enorme de trabajos científicos, es novelista. Una de las cosas destacadas que le ha pasado en su vida es que colaboró con Paul Erdős en los últimos 20 años de la vida de Erdős y tienen 8 trabajos en conjunto. Bueno, muchas gracias por estar aquí y te escuchamos.
A todos. Estoy muy contento de estar aquí con ustedes. So I will speak in English because otherwise the talk would take 2 hours instead of 1 hour. So probabilistic models in number theory, so I intend to make a short incomplete survey of probabilistic models in number theory. So the first question, since I suppose that you are not all familiar with number theory, with probabilistic number theory, is a naive question. I mean, why is not probabilistic number theory part of probability theory? I mean, this is the first question I ask myself, and actually it has a very clean answer. So, naive attempt. Let's try. So, we take a probability on n, and we say that the probability of a subset of n is just the sum of the pn's, where when n belongs to A. Okay, that's fine. Now, intuition, we want that the probability that a number is even is 1/2, that it is divisible by 3 is 1/3, and so on. This is because we want that probabilistic number theory coincide, I mean, at least we want to be compatible with intuition. Okay? Now, exercise, if you take the non-multiples of A, then you find that the non-multiples of A are, in this, if we agree on this, these are independent events. Okay, now, corollary, Pn is certainly less than the intersection of all the np's for P prime, P larger than n, because of course, if n is less than all these p's, then it is not divisible by p. But here we have the product of 1 minus 1 over p, and it is known since Euler that this product diverges to 0. Hence, Pn is equal to 0 for all n. So we cannot construct a model which is compatible with intuition and which is a part of probability theory. So we have to do it in another way. So densities. Now we take the set of integers up to n. Of course, it's a finite set, so we can take all subsets, and we consider the counting measure on this set. And we say that we replace the probability of A by the density, which is the limit of the frequency among the first n integers. Then, of course, we have lost sigma additivity. We have lost universal measurability, so that we will have sequences with no density, but we have gained the support of intuition. And, of course, we can work on, when n is finite, we work in the real probability space. Now, just to give quickly an example of a set which has no density, take the set of integers for which the first digit in base 10 is equal to 1. So this is a number between 2 powers of 10 is in the set, but of course, if it's larger than twice, I mean, we have a simple criterion for determining which numbers are in this set, And we find that if you stop at just at 10 to the k minus 1, you have a density of essentially 1 over 9. But if you stop at 2 times 2 to the k minus 1, then we have a density which is essentially 5 over 9. Therefore, the lim inf is 1 over 9, the lim sup is 5 over 9, and there is no density. But if we replace this measure by another discrete measure, then we may get a density. For instance, we can take what is called the logarithmic measure. So we affect weight 1 over n to the integer n, and of course we divide essentially by log n. And in that case, the density is equal to log 2 over log 10. And of course, it is in the between 1 over 9 and 5 over 9. And this is a general result. So the first model is Kubilius model from the school of Kubilius in Vilnius in Lithuania. And we start with approximate independence. So we look at these variable psi p, which is 1 if p divides n, and 0 if p does not divide n. And they essentially describe the multiplicative structure of n. I just ignore multiple integers which are divisible by p squared, p to the third, and so on. And if we look at the expectation, then this is 1 over p plus order of 1 over n. And if we look at the expectation of the product of two such variables, arithmetic functions but also variables, then we see that it is well approximated by 1 over pq, which is just the product of the approximation of En of psi p. So these variables are close to, they are not completely independent because there is a remainder here, but they are approximately independent. But look, if PQ is larger than n, then the expectation is 0, and this approximation has no meaning. I mean, no meaning in the sense that the error term is larger than the main term. So we have to be careful, and this we have to keep this in mind because this will come over in the whole lecture. Now, the first model for the integers up to n, the first probabilistic model, is just a family of independent Bernoulli random variables defined on a probability, on an abstract probability space, such that xp has the probability that xp is equal to 1 is 1 over p, and that it is 0 with probability 1 minus 1 over p. So that's a first model, which we know will not be completely accurate because of the large primes, but it will be close to accuracy as far as we consider events which are essentially determined by small primes. Now, additive arithmetical functions. So in this setting, a sum of independent random variables is just modeled by an arithmetic function, strongly additive because, as I said, I ignore multiple prime powers. And so we look at a function which such that f of n is just the sum of fp multiplied by xi p of n, which is also the sum for p divides n of fp. And this function, this arithmetical object, is modeled by this sum of independent random variable on a real probability space, and these are these xp's, which are exactly as described. I mean, these independent Bernoulli variables. So here we have the arithmetical situation in red and the model in blue. Now, the expectation of the model is just the sum fp over p. The variance of the model is just exactly this. And as an example, we can look at the number of prime factors. I already mentioned this yesterday. And so the expectation of the model is log n. So this is not log n to the base 2, but log n, because for sake of simplicity for the notation. The variance is also log n. And the first test to show whether our model is accurate is, can we compare the variances? So can we compare the empiric variance of the arithmetic function to the variance of the model, so of this ZFN. It is convenient to replace the fully empiric variance by the semi-empiric variance, in which we replaced, so we still look at the measure nu n, but we replace the expectation by the expectation of the model. It is harmless. In some situations it is not, but for this, in this case, it is completely harmless. So this is the semi-empiric variance, and we want to compare it to the variance of the model. Is it close? Is it dominated? Is one dominated by the other, and so on. And so this has been studied by many people since the thesis of Turan in 1934. So, well, I do not quote everyone, but the final answer is this: there exists a constant Cn which is independent of f. It doesn't depend on the function. It only depends on n, and the lim sup of this function of this Cn is 2, and the semi-empiric variance is always dominated by Cn times the variance of the model. So we have to think a little about this. What does this mean? It means that probability theory is really a good tool to study probabilistic number theory, because Cn is finite, but probabilistic number theory is not a part of probability, because Cn does not tend to 1. I mean, the lim sup is equal to 2. So there is a discrepancy. So this, in a way, is a measure, this Cn, in a way, is a measure of the distance of the two theories, if one can say so. And this is the present form of the Turan-Kubilius inequality. Okay. Now, there are many applications. If you know, when you can bound a variance, well, there are plenty of things you can do. First, apply Bjernémy-Chebyshev, of course. Now, we look at this for the random variable omega n, which is the number of prime factors, and we have this inequality with a c, with an absolute constant c. We have seen that this expectation and the variance are both close to log n. So it means that we recover the Hardy-Ramanujan theorem, which was proved in 1917 without, of course, the Turan-Kubilius inequality, and it was one of the great achievements of Turan thesis to prove it via this tool, because the proof of Hardy and Ramanujan was much more complicated, and it went through inductions, and it was quite subtle. And the proved via the Turan-Kubilius inequality is just enlightening and very clear. And it says that the number of prime factors of an integer up to n, up to capital N, is actually close to log n with an error which essentially is less than root log n times anything tending to infinity for almost all integers up to n, that is with at most little o of capital N exceptions. So it is one of the, well, in a way, I mean, it is the first result in probabilistic number theory. The paper of Harvey and Ramanujan was called on the normal number of prime factors of an integer. And it was certainly Erdős who the first saw all the implications of this result. So it is very strange. I mean, if you think of it, just that if you pick a number at random, the number of prime factors will essentially depend on the size of the integer and not on the structure of the integer. It is really astonishing. I mean, if you think of it. Of course, the number of particles in the universe is 10 to the 80 approximately, and the log is about 3. So probabilistic number theory is not a part of probability theory. It's also not part of physics. But yes, we have this result, which is really, I mean, philosophically very impressive. Now, Erdős goes further. Erdős always goes further. And suppose you have the prime factorization of a number, and k is just the number of prime factors. And now if we look at the additive function, which counts not only not all the prime factors, but all the prime factors up to the jth one, then of course this is also an additive function, and we can use also the Turan-Kubilius inequality for this. And with this, Erdős proves in a few lines that the log of the jth prime factor is close to j with an error which is not larger than j to the 3 over 4. So not only the total number of prime factors is a function of the size of n, but also you can approximate the jth prime factor only by the index. It is absolutely, I mean, it's tremendous, I mean, if you think of it. And Erdős understood this well before any other people. So yes, so I just, the size of the jth prime factor of a random integer only depends on its index. And of course, the log is close to j, or we can also say that pj of n is close, of course, to xj. But of course, the error here is in the last exponent. So so it doesn't mean that you don't have a real asymptotic here. But for here you have, I mean, it is really asymptotic. Good, so far. Now, is there a law of the iterated logarithm? As far as we are, why not? Well, the answer is yes. And Erdős actually proved this in 1946. We wrote a book with Richard Hall in 1988 and actually gave a complete proof, let's say, of Erdős' result. But his ideas were there. And you can show that the log of the jth prime factor is close to j with an error which is root 2j log j. And actually, if you replace 2 by anything strictly less than 2, then the density comes down to 0. So if with 2, the density is 1, and if you replace 2 by anything less, the density is 0. So this is the most precise approximation that you can get from the Turan, actually, I mean, from ideas which are behind the Turan-Kubilius inequality for the J's prime factor of a random integer. Now, we have the 3 series theorem of Kolmogorov, and this is this has still with the Kubilius model. The counterpart is the Erdős-Wintner theorem, 1939. It gives a necessary and sufficient condition for an additive arithmetic function to possess a limit law, that is, that the distribution functions converge weakly to a distribution function f. And this is the convergence of these 3 series. It is remarkable that even if the additive function depends on prime powers larger than 2, the necessary sufficient condition only depends on the values at primes. Okay. Now, total variation distance. So the Turan-Kubilius inequality says that this integral, which is the semi-empiric variance, is bounded by this integral multiplied by a constant Cn, which is uniformly bounded and does not depend on f and tends to 2. Now, this is, of course, not the only quantitative comparison of measures, and we can think of other ways of comparing the measures. Now, look at this distance. So this is the total variation distance. So we take the supremum over all subsets of real numbers. There is no question of measurability here. And we take here the event that f of n belongs to A, and here the probability of the model. And we ask ourselves, does this tend to 0? What is your guess? Well, so we have this constant Kn. Does it tend to 0? And the answer is no, because of the influence of the large primes. The large primes are not independent, and this kills the hope that that this total variation distance tends to 0. So we don't have such a good model if we accept the large primes. What is the next step? Well, ignore the large primes. So we take additive functions which are 0 on the large primes, and ask ourselves with Kubilius, this is the gauge of Kubilius gauge, how large can we take y to ensure that this k and y, now depending on 2 variables, tends to 0. And Kubilius in 1956 showed that if essentially if y is n to the little 1, then the density, so this u will tend to infinity, and the gauge will tend to 0. Now, of course, you know number theorists, they always want the best estimate. So this has been refined by Barbon and Vinogradov, among others. So with something tending to 0 a little more rapidly. And eventually in 1999, I gave what is essentially optimal, the optimal bound. We have u to the minus u and n to the minus 1, and both exponents are optimal. But of course, the qualitative result is already present in Kubilius result, and is very important. So if you look at if you ignore the primes which are essentially larger than n to the epsilon, then you have independence and the model is accurate. So we have a principle from this. Any statement regarding a finite sequence of independent Bernoulli numbers, random variables xp's, p less than n to the epsilon, such that with the usual probability, is equally valid for the sequence of the psi p's, with an acceptable error, provided the epsilon tends to 0. So that's simple. If you take any result in probability theory, then you can translate it into a statement regarding random variables, regarding arithmetic functions, as far as the psi p's are, the p's are restricted to be less than n to the epsilon. Example, central limit theorem, of course. So we have Sn, the sum of the psi p's, of the xp's, sorry. Then, of course, the expectation of xp is 1 over p, and the sum of 1 over p between n to the epsilon and n is roughly log of 1 over epsilon. So if it's bounded in terms of epsilon. So we have this result. And so, of course, for this sum xp, the central limit theorem is valid. But the sum of the psi p's of n is essentially the number of prime factors of n with an error which is bounded in terms of which is order of 1 in terms of epsilon. So we get with this setting, we get the Erdős-Katz theorem, 1940 in Princeton. Katz was lecturing. Erdős was sleeping in the room, and suddenly he heard that Katz was speaking of number theory, and Katz was saying that, well, he was conjecturing this result, but he said he couldn't prove it. So suddenly Erdős woke up, and after 5 minutes, he raised his hand and said, I can prove the result. And this is how, this is a true story. I know it from Erdős himself. And that, this is the second birth of probabilistic number theory, because after the Hardy-Ramanujan theorem, and we find a Gaussian law for the number of prime factors. Now, of course, we want here an error term, and Rényi and Turan. So you see 1940, 1958, so 18 years between the two. And the optimal remainder is 1 over root log n. So it's not very small, but it is optimal. And there are several proofs. One proof is particularly appealing to probabilists, since it is via the Berry-Essén inequality, which is a quantitative Fourier inversion. So if you have two distribution functions with and G is the, well, actually should be G should be how do you say absolutely continuous. Then you have this bound where the f hat and g hat are the characteristic functions. So if G is the Gaussian, for instance, of course this holds, and this you can use this Berry-Essén inequality to have a rather simple proof of the Rényi and Turan result. By the way, the Berry-Essén inequality dates from 1940, so the result could have been proved much earlier if they had used this. Now, so we have this model that I described earlier with the XPs. But actually, we can define it without any, without mentioning additive functions. We have an intrinsic definition. I will not describe the definition, but I will give the intrinsic definition of the gauge. And so we take phi of xy is the number of remaining integers once you have applied the sieve of Eratosthenes. So integers for which are not divisible by a prime less than y. And the gauge is just equal to this. So p plus is the largest prime factor. So you sum over integers, all of whose prime factors are less than y. And here you have the probabilistic approximation of this quantity, because here you assume that the primes are independent. And the gauge is exactly equal to this. I mean, it's not an upper bound or a lower bound, it's just an equality. And so it shows that in probabilistic number theory, there are two classes of integers which are of particular interest. It's sifted integers, integers with no small prime factors, and friable integers, integers with no large prime factors. So this is what we are going to study now. Friable and sifted integers. Now, as I said before, so an integer is said y friable is if its largest prime factor is less than y, and it's y sifted if its smallest prime factor is larger than y. The largest prime factor of 1 is by convention equal to 1, and the smallest prime factor of 1 by convention is equal to plus infinity. And we always have weak inequality here and strict inequality here, just because of what I'm going to say now, is that there is a canonical representation of any integer as a product AB, where A is friable and B is sifted with the same parameter. And it is very important to have, to be able to split integers into two divisors, as a product of two divisors, because very often we lack a variable. We miss a variable in number theory. So with this, with one integer, you get two, and it is very convenient. So heuristically, A is supposed to, if y is fairly large, A is supposed to behave like an ordinary integer, but more complicated, and B will behave like a prime number, but less complicated. So you have a sort of cursor that you can adjust depending on the difficulty of the problem. You can shift the difficulty between primes and friable integers. So let's start with the sifted integers, which are much better understood since many years, actually more than 2,500 years. So phi of xy is the number of remaining integers after applying the sieve of Eratosthenes. I proved in 1990 that you have this approximation. So you have here the probabilistic main term, and you have an error. And the error is e to the minus u, which records the e to the minus cu in Kubelius result. So far so good, but the main probabilistic term is wrong if u is bounded. So again, we find that large primes are troublesome. For instance, if you take y equal to root x, then phi x root x is just the number of primes between root x and x, so it's asymptotically x divided by log x. But by Morton's result, the main term is 2 e to the minus gamma x over log x, and since gamma is well known to be not equal to log 2, then you see that the main term is wrong. Now, what can we do if we want an approximation which is valid all the way? I mean, not even if y comes close to n. So we have Borstab's function, which is the solution of a difference differential equation. And then it is classical that we have this approximation. So this holds for y, for all y and x, and the main term is x multiplied by omega u minus y over log y. So this is good, but not very good if u gets very large. You want a better approximation. And by the way, this implies, I mean, because of the previous result, it implies that the omega u tends to e to the minus gamma as u tends to infinity. It is then a challenge to prove it directly just using the difference differential equation. It can be done. It's not so difficult, but it implies using some formulas of some classical formulas of Gauss for gamma, for the Euler constant. So the best known approximation is this, where it is a blend of the probabilistic approximation and the analytic approximation. So here, if u gets large, omega u is close to e to the minus gamma, and you recover the probabilistic approximation. But if u is not so large or is finite, then you recover this approximation. And this holds for all, essentially everywhere. And note that the error term here is in factor, so it is always it's always a good approximation. Now, this essentially settles the case of shifted integers. And now we will pass to friable integers. So the study of friable integers is much more recent. It was first studied in 1930 by a physicist, actually, Carl Dickmann, who published a paper in a journal of astrophysics. So let's consider the number of y friable integers up to x. So as I said, it started by Dickmann and many authors. De Bruyne, 1951, 1966. So that's the same that we spoke about at lunch. Hildebrand, and there is papers by Hildebrand, my student Eric Sayas, and many other people. And the first thing to note is that there is an easy functional equation. After all, a number, all of whose prime factors is less than y, is the product of a prime factor less than y by a number, all of whose prime factors are less than this prime factor. So you get, with this, you get immediately a functional equation. It is so evident, this functional equation, that it limited the result because people were fascinated by this equation and wanted to use it, and actually it's not the best way. So Dickmann in 1930 proved that psi xy is equal to x times rho of u, where rho is a function still of this parameter u, and rho is called now Diekmann's function, of course, and it is defined as the solution, the continuous solution of this differential equation, and it drops down very fast. So it is a characteristic of sieve problems, because solutions of different differential equations come into play. Now, for probabilists, if uj is a sequence of independent random variables uniformly distributed on 0, 1, then e to the minus gamma times rho of u minus 1 is the probability density of this converging series. So the Diekmann function actually arises in many parts of mathematics. Also, it arises in models for the stock exchange, for instance. It arises in plenty of places. Okay. Now, so we have this result of Diekmann. Now, of course, this is only true when u is fixed. So you take integers, all of whose prime factors, so integers up to x, so all of whose prime factors are less than root x, or x to the 1/3, or x to the 1/100. But we want to go beyond. So what can we do? When can we do to go beyond? And Hildebrand proved in 1984 that the validity of essentially Diekmann's result, if it is extended to y larger than log x to the 2 plus epsilon, actually this is equivalent to the Riemann hypothesis. So the study of friable integers is not on the side of number theory. It's just in the middle. It's just in the center, because studying the distribution of friable integers is essentially, it is, linked, very closely linked to the Riemann hypothesis. And Hildebrand, using another functional equation, proved in 1986 that this formula holds in this range. So this 5/3 is just the inverse of the 3/5, which arises in the prime number in the current version of the prime number theorem, linked to the 0-free region of the zeta function. So of course this is much larger than the power of log x, so it doesn't prove the Riemann hypothesis, but it shows the state of the art. And in a joint paper with Hildebrand, we got the best known approximation up to date of psi xy. So we still recover the x times rho u as a main term, and here we have an error, which is not always an error, because if y becomes very small, then u over this L epsilon of y may become large. So it doesn't prove the Riemann hypothesis, but still, it can be useful. It is still an approximation, and in particular an upper bound. The method for this avoids completely functional equations. It just uses the saddle point method. So the Dirichlet series, which is associated to friable integers, is just the partial product of the zeta function. And we just apply Perron's formula, which is a kind of a Fourier inversion formula. And here we have just the choice of the abscissa. And we will choose the abscissa according to the saddle point method. This is the equation of the saddle point. And actually using the prime number theorem, you can get approximations of alpha. And we can show that, well, there are many approximations, but the first approximation, this is the size of alpha. So if y is large, for instance, alpha will tend to 1. And if y is very small, then alpha will be like y over log y log x. So it will be very small. So, and with this, we get an approximation of psi xy, depending on alpha. But this approximation is valid for all x and y. And it has the advantage that you can compare psi xy to psi, say, x dash y, even in ranges where both of them are not understood, are not well, for which you don't have a good approximation. So this is what Erdős used to call semi-asymptotic formulae. For instance, you can show that psi of 2x and y is equivalent to psi xy if and only if y is less than log x to the 1 plus little 1. And it is, you get this, the factor 2, if and only if y is larger than any power of log x. Now, applications of the theory of friable integers. There are plenty. Friable integers, since the work, essentially since 1951 and the work of De Bruyne, friable integers are really central in probabilistic number theory now. So there is an elementary proof of the prime number theorem, which is absolutely lovely, by Debussy. He considers a model of the integers built up only from a finite number of primes. And with this, for this, of course, it is very easy to have the distribution of the primes. And with this, he can, in a few lines, the paper is 4 pages long, you can prove the prime number theorem. Applications in cryptology. Public key systems, you have 2 primes, you make the product. This is easy, to make the product of 2 primes. But if you have the product and you want to find what are the 2 primes, if these are large, then this is difficult. So you have something which is easy in one way and difficult in the other. So that's the basis of cryptology. Now, for the decoding process, you need a factorization method. And friable integers are easy to factorize. So that's why friable integers are important in cryptology. Algorithmics, problem of the discrete logarithm. If you have the multiplicative group modulo p, and you have n, and you want to know what is the exponent. If G is the generator of the group, you want to know what is the exponent corresponding to n. And there is a proved solution in running time T of p, with this T of p using also friable integers. The circle method, additive problems. You want to solve n as the sum of s integers belonging to certain sets. Goldbach corresponds to the sets equal to the set of primes. Waring's problem, the set of case powers. And the method, which was devised by Hardy and Littlewood, consists of expressing the number of representation as an integral on the circle. So that's why it's called the circle method. And the friable integers have good factorization properties, and this leads to good estimates for the exponential sums. So it's again, it is useful in this theory. Another thing which is very interesting is summability method, friable summation. This was defined by Duffin in 1957 and rediscovered by Fouvry and myself a few years later. Instead of summing a series according to the size of the index, we just sum according to the size of the largest prime factor of the index. So we say that the series has friable sum S if the sum where the integers are counted, I mean the largest prime factor is less than y, if it tends to S as y tends to infinity. Example, you take this series. Now we know we can actually compute the limit, and the limit is not what you expect. What you expect is this log without the m of theta. But actually, if theta is a rational with a prime power denominator, this m of theta is not 0. So it means that the summability method is not what one calls a regular, because you have a series which are converging in both senses, but not to the same limit. So it's not a regular process. And if a series is summable, but with, excuse me, I have to drink some water. If a series is summable, and if both sums are equal, then we say that the series itself is regular. And actually, it can be shown very easily that the friable regularity of the sum of mu n over n, which should be equal to 0, where mu is the Möbius function, is equivalent to the prime number theorem. So friable summation, again, is rather central in number theory. And we have a recent result with La Bretèche that friable summation of Fourier series verifies Jordan's theorem, but avoids the Gibbs phenomenon. So it's very interesting. So in other words, if you have a function of bounded variation normalized on the torus, then the Fourier series is regular with respect to friable summation. So it is a sub-series of the full series, and it does tend to what you expect, but the supremum also tends to the supremum. You have no Gibbs phenomenon. So this is very useful. It could be used in waves, in approximations and so on, because I think it is the only case of a sub-series which converges to the full series without the Gibbs phenomenon. And if you know that f is Lipschitz, then you have an effective bound. There are plenty of applications. For instance, if b is the first Bernoulli function, so that's fractional part of t minus 1/2 and 0 on the integers, then this series converges if and only if you have this series converges where the qj's are the denominators of the convergence of theta. And well, okay, I will leave this. Now, Billingsley's model. Now, Billingsley in 1972 devised a model of the large prime factors of an integer. So if you order the prime factors in decreasing order, then this vector, considered as a random vector on omega n, equipped always with a uniform probability, converges weakly to a Poisson-Dirichlet process with parameter 1. So a Poisson-Dirichlet process is well known to probabilists, but one way of constructing this is you take uniformly distributed random variables independent on 0, 1. You consider x1, x2 is 1 minus u1 times u2, and so on. So algebraically, this is equal to 1 almost surely. Now, you rearrange the xy's because they don't have to be decreasing. You rearrange the xy's in decreasing order because, of course, this is a decreasing, I mean, the coefficients are decreasing. And the law of this rearrangement is the Poisson-Dirichlet law. Now, and the probability that if you have a sequence obeying the Poisson-Dirichlet law, then the probabilities here can be expressed using the Dickmann function. Completely explicitly. In the year 2000, I gave an effective result of Billingsley's result with an error term, which is optimal also. Now, the friable Turan-Kubilius inequality. Now, you have you know, in the Kubilius result, in the Kubilius model, you ignore large prime factors. So suppose now that you want to study the Turan-Kubilius inequality, but for those additive functions which are 0 on the large prime. So in the definition of Kubilius gauge, here we have a measure which emphasizes small integers, because you have here the phi of capital N over little n. But suppose you want to emphasize no integer particularly with respect to others. So you take uniform measure instead of this measure with a weight. And you get this, I have to run because of time is running. But you get this form of the Turan-Kubilius inequality. And now we know that in the classical case, the best constant is 2. But what happens when you get the general situation? So, okay, well, I have to switch this because, well, let's say that the answer will be yes. You have the supremum is finite, and you get here something which matches the Kubilius model. If y tends to infinity and u tends to infinity, then the constant in the Turan-Kubilius inequality will tend to 1 now. So it matches completely probability theory. And the value of the constant, if y is a power of capital N, then the value of the constant becomes, I mean, is a function which can be explicitly computed from the spectrum of a non-compact Hermitian operator. And we have a paper with Bruno Martin and Enro, where we actually found a table for this function, and this function is actually not decreasing. Okay, so no, I will pass about this. So other probabilistic methods, I will just, how long? 5 minutes, is it okay? Who is the? Saira? 5 minutes. So Cramer's model. So what is Cramer's model? You know that the number of primes is about the logarithmic integral of n. So 1 over L, 1 over log n will approximate the probability that an integer of size capital N is a prime. So the wonderful idea of Cramer is to say, okay, let's consider a sequence of independent Bernoulli random variables with this probability xn is equal to 1 with probability 1 over log n. And with this, we construct a random sequence. Now, the general conjecture that Cramer makes, the principle, is that if a property is almost sure for the random sequence, it should be shared by the primes. Wonderful, I mean, simple. So with this, one can make plenty of conjectures. The first thing is that if we look at the law of the iterated logarithm, we will know that the number of integers in the random sequence up to n is close to the logarithm of to the integral logarithm of n, with an error which is of this size and an oscillating term. And Littlewood actually proved something which is not exactly the same, but he showed that for the primes you also have an oscillating factor. The Riemann hypothesis, of course, gives something better. However, Cramer's model implies that n and n plus 1 are both primes for infinitely many n, which, after a little thought, can be understood to be not true. So we have to modify the model to make it more accurate. And we modify it in this way so that the probability that a number is prime, knowing that all its prime factors are larger than some fixed number z, is equal to this. And with this model, this leads to the refined Cramer conjecture about the distance between consecutive primes, which is the current conjecture for consecutive primes. And Zhang and Ménard, proved recently that the lim inf is finite. And as far as large differences, we have this result with Ford, Green, Konyakin, Ménard, and Tao. So we are still far, from Cramer's conjecture, but not that far. Now I will end with local laws, and this is by Seith and Selberg. So there exists a holomorphic function which is 1 at 1 and at 0, such that the number of integers with k prime factors is approximately, follows approximately a Poisson distribution multiplied by this smooth coefficient. And Erdős proved that the distribution is Poisson is any sufficiently long interval. I think my time is over, so I will stop there. Thank you.
Bueno, me parece que se hizo un poquito tarde. Quiero que las preguntas las puedan hacer a Gerald los que quieran, que él va a estar aquí un rato más. De paso, quiero contar que hay dos invitados franceses en este momento, que es Julien Clement y Loïc Lot, de Université de Caen, Francia. Están dando un curso sobre análisis probabilístico de algoritmos, que en particular una de las clases es mañana, viernes a la mañana, y hay un par de clases más. Bueno, eso es todo. Entonces, sí, agradecemos a Gerald otra vez.
Gracias.
Thank you, folks.